Welcome back. In this third series for week 2, we will look at 3 applications. And first of that application is the traffic problem. We have alluded to this problem during the first week. So, there are 4,000 motorists or autonomous Tesla vehicles. They have to travel from A to B. A to C is congested road. The time taken to travel from A to C depends on the number of autonomous vehicle on that road, and let us say if it is X, then time taken is X by 100. C to B is quite wide, so it takes 45 minutes. A to C is like C to B, here it takes 45 minutes, and D to B is like AC, it's narrow congested road, and if there are X motor vehicle on DB, then time taken to travel from D to B is X by 100, but this we had discussed during the last week. If you think about who are the players, so then 1, 2, 3 to 4,000, of course they may have a name, but we can represent them here by simply numbers. So these motorists, they have to decide, they are the decision makers, either a human decision maker or an autonomous machine decision maker that's deciding. Strategy set or action set for each player, each motorist is either to follow ACB and ADB, either go this way or go this way. What is the payoff? Payoff of negative of time taken. Why I say negative, not positive? The negative because we want it to be as less as possible. It's possible we can say 1000 minus negative of time taken. Nothing would change, but now it will be a positive number. If time taken is more, payoff would be less. So as we have shown that when we talk about utility, it's ordinal in nature. Rank matters, not the exact value. But that's not always the case. When utility is coming from money, more money is meaningful in a way to describe, define, but here we are just talking about rank for a particular person. 10 rupees is more than 5 rupees, even in place of 10, if it was 9, it would have been more than 5. So rank is important. What would be the Nash equilibrium of this game? So Nash equilibrium of this game will constitute an action or a strategy for each of these 4,000 players. And so how to obtain? We cannot make, even though each one has only 2 strategy, but you will need 4,000 dimensional table, which is impossible to make. So how to go about it? One way would be to propose something and check whether that is Nash equilibrium or not. How can we check? We will allow one of the drivers to change his or her behavior and see whether he or she becomes better off or not. If none of the drivers could become better off, then we would say that it is a Nash equilibrium. So here is a proposal. We don't know, there are many possibilities, but in one, this is such that action profile that 2000 of drivers take A, C, B and 2000 of drivers take A, D, B. What would be the time taken to these 2000 drivers? It's going to be X by 100. So 2000 by 100 plus 45, this is going to be 65 minutes. And here again 45 plus 2000 by 100, that is 65 minutes. Again, there could be several different ways, several different action profile that would satisfy this criteria. I am saying all those action profile that satisfy the criteria that 2000 of them are taking this path and 2000 of them are taking the other path would be a Nash equilibrium. So there are many Nash equilibrium. Let us check whether it is true or not. Let us say one driver who is on this path, can he do better? Let us say, how can he do better? If he changes to this way, what will happen? Of course, here X will reduce. That is not important. We what is important for this driver, that he is changing the path and what is happening to his payoff. So now x will go up to this, x will go up to 1000, 2001. Already there were 2000 vehicle, one more is coming. So 2001 divided by 100, and here is 45 minutes, and this is 20.01 plus 45, and that is 65.01. Earlier it was taking 65 minutes, now it is taking 65.01 minute. So clearly this driver doesn't have any incentive to change his action from ADB to ACB because it increases. We can do exact the same exercise for one of the motorist here who is taking ACB and change his action to ADB. Again this will become 1001. Remember, when we changed this motorist, everyone else was doing exactly the way they were doing earlier. Now when we are changing a driver here, we are keeping that 2000 of them were earlier driving through ACB and 2000 of them were driving through ADB. So the only change is, because of this driver, now only 1999 are driving this way and 2001 are driving this way. Again his time taken will go up from 65 to 65.01. So he doesn't have incentive, and all other 2000 drivers are like this driver, they would follow the same math. 2000 drivers are following this way, ADB, they will have exact same logic. So none of the drivers can unilaterally deviate and increase his or her payoff, and therefore none of would like to deviate, and this would be a Nash equilibrium in which 2000 drivers are taking path ACB and 2000 drivers are taking path ADB. Now how did I figure out 2000? It looks symmetric, but that is not important in a way, because in Nash equilibrium we can check one of the ways. But another thing we can say, let us say if x are taking ACB, then they are taking x by 100 plus 45, and if x are taking ACB, then 4000 minus x are taking ADB, then the time taken for them is 45 plus 4000 minus x by 100. If this happens to be more than this, then all the drivers who are taking path ACB will have incentive to change to ADB, and if this is more if this is less than the second one, then the drivers here has incentive to change their path. So in equilibrium it seems this entity and this entity, they should be equal. So I can say 4000 minus x by 100 has to be equal to x by 100, and when we solve it, x will come out to be 2000. That's how I can figure out. But this is not a paradox, this is just we have solved the game. Now let us say there is a modification in the game. The government figures out that the C and D are very close to one another. In fact, there is just a narrow river in the middle. So government builds a bridge from C to D, and but because of financial budget constraint, they were able to build very narrow bridge. Let us say time taken from C to D is 0 minute. Nothing would change if you take 0 this time to 1 minute or 2 minutes, but let us for simplicity keep it 0. Now what would happen in this setting? So who are the players? Again 1, 2 to 4000, these are players. What are the strategies? Each driver has a strategy or action to follow path ACB. They also have a strategy to follow path ADB as earlier. Now there is a third possibility, go to A to C, come to D and then go to B. So A, C, D, B, these are the three possibility. What are the payoffs? Again the payoffs is negative of time taken. Now what are the Nash equilibriums? Can we figure out Nash equilibrium? Can we have the earlier Nash equilibrium in which 2000 were taking path ACB and 2000 are taking path ADB. Let's say this was the earlier pattern. What would happen? Let us say the person, that motorist who is taking ACB, if he changes from ACB to ACDB. ACB they are taking, let's say earlier, this is the case, they are taking 65 minutes. But if they change to ACDB, AC part will take 2000 divided by 100, CD will take 0. You want to take 2 minutes, 5 minutes, nothing would change, and then D to B will again take 2000 by 100. So this comes out to be 40 minutes. Time taken will reduce from 65 minutes to 40 minutes. Of course, they would change their behavior. Driver here would change their behavior. In fact, people who are following ADB, they would also like to go to ACDB unilaterally. They will deviate. So this can no longer be an equilibrium. So I want you to pause the video and think about it. What would be the equilibrium in this setting? Notice one thing I want to say, that C and D are basically now 1 point as it is taking 0. Okay. So unless there are, if there are all 4000 vehicle taking AC, what would be the time taken to cross AC? 4000 divided by 100, that is the 40 minutes. So this is 45 minutes, which is more than 40 minutes. So no one is going to take this path. Everyone will prefer AC to AD, because literally by taking AC they reach to the same point. And same here, if everyone is taking this path, they are taking 40 minutes and this is 45 minutes. So going from D to B is much easier, then takes much less time than going C to B. So now there is only one Nash equilibrium in which all drivers are following ACDB. What is happening as a result? The time taken goes up from earlier 65 minutes to 4000 by 100 plus 4000 by 100, and that is 80 minutes. In the new equilibrium, everyone follows the ACDB and they will take 80 minutes. Let me say a few things. I want you to spend some time with problem and make sure that you understand that this is the only Nash equilibrium. There is no other Nash equilibrium possible in this game. So am I saying that whenever bridges are built, the time taken increases? No, that would be very wrong interpretation of this setting. Here the structure is such that building bridge worsens the traffic situation and motorists end up taking more time. Most of the time building bridge alleviates the reduces the travel time, so it's always welcome. But we have to be wary. We cannot blindly build the bridge and think that it will help the traffic. Sometimes it can create problems in the traffic, so we have to be very mindful. And that's what is the Braess paradox a German engineer had figured out. So some example let me give you, that in Germany in 1969, after that Braess had figured out that traffic worsened until a newly built road was closed. In New York City on Earth Day, 42 Street was closed and traffic situation had improved. In Seoul, Korea, a 6-lane road was torn down to improve traffic flow. So this is a very important, and it's not just in traffic you see, you also see exactly the same problem in internet traffic as well as in electricity network. So one has to be very mindful. One should not be spending resources blindly to build something, because building may not necessarily help solve the problem. So that we have to be careful about. So that's it about Braess paradox. See you in the next video.